This lesson is part 1 of section 4.2. We're going to be talking about the binomial theorem. What we're going to be doing for today, though, is using Pascal's triangle, something that you probably are familiar with already from last year in 90s, to complete a binomial expansion. So just to refresh your memory, I have the first 6 binomial expansions. So if we were to find a plus b to the 0 power, we would get 1. A plus b to the first power, we get a plus b, and so on. So you can clearly see all these terms here worked out. And basically what we're looking for are some patterns. Now, when you look at the patterns here that occur in the expansion of a plus b to the n, you're going to notice that there are always n plus 1 terms. So something like a plus b to the 5th is going to have 6 different terms. The expansion begins with a to the n, and it ends with b to the n, and the sum of the exponents for each term has to be n. So in other words, each of these here adds up to 5. So we have to the 5th power, here we have 4 plus 1, here we have the 5th power, again 2 plus 3, 1 plus 4, and really it's a to the 0, b to the 5th to give you 5 again. The exponents will decrease by 1 from each term. So for your a term, so this should say the exponents of a and the exponents of b decrease, but the a term here decreases in exponents as you move term to term, okay, until finally it's a to the 0. And your b exponents increase, so we start at b to the 0 and we work our way up. So it's b to the 1st, b to the 2nd, b to the 3rd, b to the 4th, b to the 5th. When n is even, you are symmetric about the middle term. So 6 is the middle term here, and we have our coefficients. They are symmetric. We have 1, 4, 6, 4, 1. When n is odd, so to the 5th power, they're symmetric about the 2 middle terms. So we have 1, 5, 10, 10, 5, 1. So there's the symmetry here. Okay? So if we take a look at just the coefficients of that binomial expansion, a plus b to the nth power, we're going to see this array of numbers here. Okay, this is known as Pascal's triangle, something that you probably looked at last year. And just to help you refresh how you can find Pascal's triangle on your own, you are always going to have a 1 to start with, and your first row is pretty easy. So this is the row a plus b to the 0 power. Okay. Your next row, a plus b to the 1st power, is that row 1, 1. Now, so to the 2nd power here, to find the coefficients here, 1s are always going to be on the outside, but now we just add these 2 terms here to get 2. And then for the resulting row for a plus b to the 3rd power now, so that was a plus b to the 2nd. For a plus b to the 3rd power, I simply add 1 plus 2 together. So I have 1, 3, and then 2 plus 1 together to get 3, 1. So you just have to add the diagonal numbers to figure out what that next term is. So a plus b to the 4th power is going to be 1, 4. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4, and then 1. And you do see that symmetry here as well. It's symmetric about that middle term. So you can do this for an infinite number of times, obviously. It's just very tedious to do that. Now, what I think is really sad, if you read here, the triangle was studied by Pascal, who was born in 1623, but this had already been sort of described by Chinese mathematicians centuries earlier. So it's not credited at all to this guy. I can't pronounce the name, but Yang Wei? I don't know. I'm just guessing at it. He had come up with this, 500 years earlier, even though now it's known as Pascal's triangle around the world. In China, they give him credit at least. So, feel bad for the dude. So Pascal's triangle is a really nice way for us to do some binomial expansions when they're of small degree. However, when they get very high, like if I asked you to find a plus b to the 47th power, for you to have to sit there and draw out the array of numbers here and try to find the 47th row, that would be kind of crazy and very tedious, very inefficient. So we look for another pattern that's useful for doing an expansion of a very high power. So here in words I have that the coefficient for any term can be generated as follows. You're going to look at the previous term, so you have to make sure you know what the previous term is. What you're going to do is multiply the coefficient by the exponent of a. Okay? And then you're going to divide by the number of the previous term. So you're going to take the previous term's coefficient and multiply by the exponent of your first term, your a term. And then you'll divide by the number of that previous term. So if it was the first term, you would divide by 1. So I'm going to do an example with you so this makes a little bit more sense, but we're going to basically compute the second and third coefficients for this expansion of a plus b to the seventh. So what we have to do in order to compute the second and third coefficients is actually refer back to the first and second terms. So in this case, we'd first have to find the coefficient of the second term by referring to our first term, a to the seventh. We know that it would be a to the seventh because the first term is always a to whatever that power is. Okay? So we take a look and we know that this is 1, a to the seventh. So I'm going to use the coefficient of a. This is the coefficient of a. Okay, this is, again, right here, it says multiply the coefficient, okay, by the exponent of a. And the exponent of a here is 7. So this is the exponent of a. Now we would divide here by the number of the previous term. So that number of the previous term is term 1, right? This is the first term. So that's why we're dividing by a 1 here. Now we get 7, which makes sense because the next term would be 7 times a to the 6th power times b. All right? Now to find the third term, what we're going to have to look at is the second term. So you always look at the previous term. The second term was 7a to the 6th times b. So what you're going to do is take the coefficient. Remember, this is just the coefficient of the first, or of the, sorry, the second term. So this 7 here. So it's the coefficient of the previous term. And then the exponent on the a term. So we kind of ignore the b entirely. And then here, we're going to divide by the term number. This was the second term, so that's why we're dividing by 2. So our next coefficient should be 21. So our third term has a coefficient of 21, and since we know what the binomial expansion here should be, it's going to be 21 a to the 5th times b squared. Okay, so this is a little bit helpful, that we're going to get into this when we start talking about binomial theorem. All right, so I just wanted to cover that. But when we're going to do these practice problems here, we're actually just going to use Pascal's triangle. All right, we're not going to go through that method I just showed you. We're just going to use Pascal's triangle. So we're going to expand here to the 4th power. So what I'm going to do is draw out my triangle so that I know I'm using this 4th row here. And I should have coefficients 1, 4, 6, 4, 1. So this means I should have 5 total terms. So 1, 2, 3, 4, 5, that makes sense here because it's going to be n plus 1, so 5 total terms. All right, now, what I actually like to do when I set this up is draw out little placeholders here so that I remember that I want to put coefficients in front of everything. So let me erase here. Okay. All right, so now I'm going to work on the term here by looking at the a term. Remember, this is just a, and this is b. Now, notice that b is actually -2, though, so that's going to change some stuff here. But when we're working with the a, we're just going to take x to the 4th power, and then it's actually -2 to the 0 power, which I'm going to eliminate here, just not even write that in, because I know that's just equal to 1. But then the next term, remember, when you go to the next term, the a term goes decreases by 1. So the degree here decreases by 1. So this is now x to the 3rd. And then that b term, -2, will increase. Now it's to the 1st power. Okay. As we move, again, the a term's exponent will decrease by 1. And the b term will increase by 1 as well. So basically, you're just following a pattern now. You want to make sure you get that pattern correct. Here I'd have x to the 0, so I'm going to skip that, and -2 to the 4th. So always make sure, one of the things I'm going to look for is to make sure that your exponents always add up to 4. If they don't, to me that's a pretty big deal that you don't really understand the concept, so please make sure that you're always checking to see that your exponents add up to the degree that you're expanding this binomial. Now, from here you're going to simplify, okay? So why I put this in parentheses is because sometimes you guys might read this as 4 times x cubed minus 2 to the 1st. And then people end up with 2 different terms here. So instead of having 5 total terms, they end up with 6 total terms because they read that negative sign as a subtraction. So it's all those little things that kind of cause issue. So make sure that you put that in parentheses, especially when you have a negative, because you want to make sure that you're taking that to whatever power. So it also, because it's negative, will affect the sign in front of your coefficients as well. So there's all these really little things you have to be really careful about when you're doing a binomial expansion using Pascal's triangle. All right. So let's go through and try to simplify. This first term is basic. It's just x to the 4th. The second term, though, instead of being a positive term, it's actually going to be negative 2 times 4. Negative 2 to the first is negative 2 times 4 gives me negative 8. So instead I'm going to write this as minus 8x cubed. Now the next term, this is actually going to give me a positive 4. So I have positive 4 times 6, 24, and then that x squared. For the third term, or fourth term, sorry, I will get a negative here because negative 2 to the 3rd power is negative 8, multiplied by 4 is negative 32, and the x. And then the last term here, negative 2 to the 4th, is going to give me a positive 16. So I want you to take a look at 2 different things here. One, I have 1, 2, 3, 4, 5 terms. So I always check to make sure that my terms end up being correct. Okay, but also notice that the sign changes. It goes positive, negative, positive, negative, positive. That's going to happen. You're always going to have a sign change here for every other term when you have a negative value for your b term. Okay? So that's the first expansion. I'm going to do one more with you, and then I'll let you guys practice the last one on your own. The last one does have a negative, and it's a pretty large one. This one's pretty tricky, so check the key after you're finished. All right, so for the 6th row here, I'm going to quickly draw out Pascal's triangle. And I really don't have much of these memorized. I mean, I guess after you do it for a while, you'll sort of be forced to memorize some of them. But really, I'm just adding, the diagonals like I showed you before. So anyhow, here is this row that we want to use. It's the 6th power here. So we know our coefficients now, and I'm going to do placeholders here. So let me erase everything. So I have 1 times something plus 6 times something plus 15 times another term plus 20 times another term. Let's give me some more space there. Plus 15 times a term, and I'm going to come down here and do the plus 6 times a term, and then the final term plus 1 times that term. So I really like to set up this placeholder thing because I think it just makes the work a little bit clearer for you too. Alright, now the first term should be my a term raised to that power. The b term is 2y to the 0 power, which is just 1. So be careful here that you're not just raising the x to the 6th power, but you're raising both the 3 and the x. Okay, so put that in parentheses. I really think you should always put parentheses around your a and b terms, especially when it's not just a single variable. It's got a constant in front of it. If it has a coefficient, make sure you put it in parentheses. Okay, next. The next term here should be 3x to the 5th power. It will decrease by 1. And our b term, the 2y, will increase by 1. So notice here again that my exponents add up to 6. For the next term, I should have 3x to the 4th power, 2y to the 2nd power. And the next term will be 3x to the 3rd power and 2y to the 3rd power. Then 3x to the 2nd power and 2y to the 4th. Then 6 times 3x to the 1st power and 2y to the 5th. And finally just 2y to the 6th power here. So notice again that I always want to check to make sure that my exponents do add up to 6, and in fact they do. I also have 7 terms right now, so I should only have 7 terms in my final answer. Okay, always be careful to check for that, especially when you have a negative for your a or your b term. Okay, and then from here, it's obviously just straight up computation now. The reason why I want to make sure that you write this in parentheses is because we have to take 3 to the 6th power. So my first term here is 729, x to the 6th. Now my next term is going to be 3 to the 5th power multiplied by 2 multiplied by 6. So you always want to simplify everything here. So let's work on each of those. I'm not going to do every single computation here because I think after you do like one of these you should get the idea. But basically you take your 3 to the 5th, so 243 multiplied by 2 multiplied by 6, and then you're going to use your exponents here for the x to the 5th. Sorry, not use your exponents, but distribute your exponents, and then y to the 1st. Okay? So here you would evaluate that. I'm not going to do that with you right now. You would be able to use a calculator though, so you just evaluate that. Alright? Okay, so I don't want to continue just to do simple computations with you, but basically the idea here is to make sure that you are always distributing the exponent to each term and then multiplying it by the coefficient. Don't forget to do that to the coefficient out in front. So really it's just computation from here on out as long as you understand the method. So I'd like you to try number 3. You can actually just finish off this one if you want to do that and check with the key if you want to try an extra one though. I think this is the toughest one here because we have a negative base here, so you should see some sign changes here as well. So that's the end of the lesson. I will see you in class tomorrow.